let us start this lecture with a thought process and remembering that man is a curious and creative creature by nature, but of course with the modern life people don't have time to think. And let us recapitulate that what we learnt in the last lecture. In that we started with what you call the properties, and we looked at when it can be an exact differential so that we can call a variable as a property. And later on we moved into the kinds of properties, intensive property and extensive properties, and also the specific property, right? We defined and we took some examples which will be helpful for analyzing thermodynamic system. Then we looked at the pressure and what its importance, so also the how to measure. I have just touched upon some of the things, and you should learn it, how to measure. And today what we will be doing, we will be looking at various forms of energy. And let us ask a question, what do you mean by energy? And all of you know that it is basically the ability to do the work, and there are several forms of energy that exist in nature, like your kinetic energy, potential energy, thermal energy, mechanical energy, chemical energy, nuclear, and so on and so forth, right? Now this energy, if you look at, we will be dealing with. Now it can be classified into various forms, but the sum of all the forms of energy, we can use a symbol known as E. You can use any other symbol as a matter of fact, but generally people use E, and that unit will be in SI kilojoule. It can be megajoule, kind of things, or a joule simply depending upon the amount of energy what you are dealing with. And specific total energy, E by m, kilojoule per kg. If you recall, the energy is basically an extensive property, whereas the specific total energy is what? Intensive property. Am I right? Because per unit mass. So as I told that this energy can be broadly classified into two categories. One is macroscopic form of energy, other is microscopic form of energy. And microscopic form of energy will be related to what? Related to the molecules, atoms, and their their activities, the extent of activities, whereas the macroscopic form of energy will be possessed by the system with respect to outside reference frame, right? And that what we will be dealing with in this thermodynamics, right? But however, let us look at it also the other aspect of the microscopic energy we will be discussing little bit. And the common form of macroscopic form of energy are basically kinetic energy and potential energy, right? So let us look at kinetic energy, and we will take an example. Let's say a car which is moving with a certain velocity v, right? It is moving with certain velocity v. And if it is moving with certain velocity, it will be, that means how it will be moving? Somebody should be applying a force. Am I right? Otherwise it won't move, right? Anything which is, that means the car has to displace something. So we know according to the Newton's second law, the force is basically is equal to mass into acceleration. When it is velocity, it will be either at a constant speed, or it will be accelerating, or it will be decelerating, right? It can be anything. But let us say that force basically will be mass into acceleration, and the work done will be nothing but your force into change in length. If it is basically doing, there will be this, moving, car will be moving certain distance, let's say dl, and then will be f dl, and f is nothing but mass into acceleration. And if you look at this, acceleration is nothing but change in velocity with respect to time, right, dv by dt. And if you look at this dl by dt, if I just take this is nothing but your what, right? So this is nothing but your what? That is nothing but your velocity itself. So usually mass into velocity into change in velocity between station 1 to 2, you can say, and then if you integrate, keeping this mass is not changing, like, then it will be the work done is basically m delta v square by 2, and that is nothing but your kinetic energy, right? And this, what is the reference for this? With reference is with respect to the road, right, isn't it? So that means that all the displacement, whatever we are doing, the velocity, acceleration, we are having reference to the road, right? So this kinetic energy was coined for the first time by Thomas Young in 1807, and later on it was used by Lord Kelvin in thermodynamics around 1856. Of course, the kinetic energy per unit mass will be nothing but your delta V square by 2, it is joule per kg, and this is a specific kinetic energy, right. So let me take another example, right. You might have observed lot of construction work is going on in our campus, am I right? Okay. So I think few years back I observed a person is standing on the ground, and there is a one floor kind of things, right, and there is another person standing, okay, one laborer, and he is throwing the brick towards the person who is standing on the first floor, okay, and he is catching. So what is happening? That brick, so a person will be throwing a brick and another person will be catching. So that means it will be throwing with certain velocity, that means certain kinetic energy, therefore it is moving, yes or no? Am I right? Okay. So then once it will keep there, right, or that person, that means this kinetic energy, what will happen when that person will catch or about to catch? What will happen to that energy? That means velocity will coming to the zero almost, right? So what will be that energy? Kinetic energy. Will it be kinetic energy will be there when the person is about to catch or already caught? No, no. So what is that energy? Where the energy has gone? Potential energy, right? And that, what is the frame of reference? Frame of reference is you fix a coordinate system in the floor and then you talk about it. Now, this is, I have seen in this campus during winter season, right? And a poor fellow laborer who is doing this job, which was quite risky. Suppose that person will lose his concentration, who is trying to catch it, which is coming with a velocity, very, right, and a mass, what will happen to him? He will be hospitalized, am I right? Now, question arises, I am posing a question to you people. As an engineer, can you think of something so that that kind of risk you won't get? Okay, there comes into picture the thermodynamics, how to analyze and what is the way of doing that. That means you need to be sensitive to the people's need so that you can devise a proper device such that the problem of people can be solved. So that is the engineering aspect one has to think. So a sensitive person can be a good engineer. Am I right? So coming back to that potential energy, you have already talked about potential energy. You might have seen in this place there is a lot of trees are there, right? and some of you might be in the southern part of the country, right, where there is a, let's say, coconut tree, very tall trees. Coconut trees are very tall earlier days. Nowadays with the hybrid it became small. Okay. Now let's say the coconut is attached to the tree. What will be its potential energy at a very height, let's say maybe 4 meter kind of thing, or maybe 5 meters, right? What will be its potential energy? Potential energy I am talking about, because we are discussing about potential energy. What will be? Will be 0, because it is attached. But let's say by due to something or somebody cut it, then it is falling. What will happen? It will be gaining, but just after getting cut, it will be having a potential energy which is equal to the height, whatever it is there. Am I right? So, and then after that, when it will fall down, it will be gaining kinetic energy. That means potential energy is converted into kinetic energy. So if you look at, there is a mass which is having a velocity v1 and mass of 1 kg. It is falling down and and reaching the J2 with a velocity v2 and m2 is equal to 1 kg, of course the same mass. So we need to find out potential energy. So potential energy basically mass into g, that is the acceleration due to gravity, and change in the elevation, right? And that will give you the potential energy. And the potential energy, if I take this in this example, that mass is 1 kg and g is 9.81 meter per second square, and Z1 minus Z2 is nothing but 1 meter, it will be something 9.81 joule you can get from this example what I have taken here. So the potential energy was basically coined much later by Rankine, William Rankine, who was a pioneer in one of the stalwarts in thermodynamics in 1856. And of course the specific potential energy is nothing but your potential energy per unit mass, that is equal to the G into delta Z, what is change in elevation basically. So if you look at, these are the kind of energy what we will be dealing with, kinetic energy and potential energy. Potential energy will be also various kinds. It's not this potential energy what I have just now discussed is based due to the gravitational effect. There might be magnetic effect, there might be other effects, right, kind of things. So potential energy will be various kinds kind of thing. And these quantities, what are the quantities involved in this? We have seen is basically mass, velocity and acceleration kind of things, right? And these are observable quantities. You can observe, you can measure it very easily, right? And these are the energy, when you talk about it is very easy to quantify it, because you know the properties associated with and observable quantities, so that you can measure it. So what are the other forms of macroscopic energy? Any idea? These are all very common, people will be knowing. But what are the others? I have already talked about it, like what I told, electrical energy, like magnetic, surface tension and several others, kind of things will be various other forms of macroscopic energy one can think of. So we will be dealing mostly with the macroscopic forms of energy in the thermodynamics, right? But however, I will just try to give you the flavor of the various microscopic forms of energy we will be discussing now. So this is, as I told, related to the molecular structure, like how it is, let's say whether it is a monoatomic or diatomic or polyatomic or triatomic molecules, and what are the its interaction with themselves, like basically degree of the molecular activities will be important for this energy, right? and all the material will be consist of large number of particles, what we call molecules, atoms, ions, electrons and other things, and all will be basically possessing some energy, and those energy is known as microscopic form of energy. So all these particles are in all the time in motion, right? They will be in a continuous motion and possessing some form of energy. So these things, these forms of energy is basically can be think of, let's say that is a what you call a molecule, right? Which if it is there having, let's say this is having x direction, right? Let's say this is x direction, this is y direction, this is z direction, and this can translate. This molecule can move from one either in x direction or y direction or z direction, right? And this, whenever it is moving with particular directions or kind of things, it can be known as the translational energy, because it is moving, and as it is moving it will be possessing certain kinetic energy, and this kinetic energy is basically known as the microscopic form of energy. For example, I am considering a molecule, and then molecule having mass m and it is moving with a velocity v. Keep in mind that this is, don't think this is not that each molecule will be moving with the same velocity. For example, if I take a cylinder, is it each molecule will be moving at same velocity? No. Maybe mass is same if provided the molecule is same. Let's say nitrogen gas cylinder, right? And the motion also will be very random. It will be colliding each other. So it may go and bump into the wall, or it may go and collide with another molecule. Of course, if it is inert, no reaction is taking place, right? Kind of thing. So therefore, these will be different. I have just considered for a single molecule, therefore I am writing this. Otherwise, it will be each molecule having different velocities. Maybe mass is same if the molecule, the gas is same. So, and if you consider, there might be diatomic or polyatomic molecule which can rotate. Like molecule can translate, it can rotate, right? And rotate about center of mass. So therefore, that will be basically rotational energy. You can think of moment of is equal to I omega square by 2, and I is the moment of inertia about the center of mass, and it is rotating with the certain angular velocities. So you can calculate for each molecule, then you think of about whatever the number of molecule it will be having in a system, then it is very complex, and you will have to look at. So that is basically the rotational. If you look at, there is another rotational kinetic energy. That means molecule will be having kinetic energy, molecule will be having rotational energy, and the molecule can also vibrate within certain mean position. With this certain mean position, it will be vibrating, right? If it is vibrating, that is known as vibrational energy in a microscopic form. That means particularly at low temperature, like energy of gas is mostly due to the translational and rotational, right? But high temperature, vibrational modes contribute more to the energy of the molecule, because if you look at microscopic energy, it will be sum of all rotational and kinetic energy and vibrational energy, right? And so what we call this total energy, that means total basically translational, rotational and vibrational energy, we call it basically kinetic energy of the molecule, because it is motion, all the time motion, and that we call it as a sensible energy. Why you call it sensible energy? Because we can measure it. We can measure in terms of, let's say, temperature and other things, right? So therefore we call it as a sensible energy. But however, the portion of internal energy associated with the kinetic energy of molecules is known as sensible. This is a little more definition what we are given, because these are all internal energy, right? This is one form, because due to the motion it will be, this energy is coming. Therefore, we call it as a kinetic energy of the molecules. And if we just sum it up, that translational energy and rotational kinetic and vibrational kinetic, that is nothing but your sensible energy, and we call also in case of sensible enthalpy, right? We will be dealing with that. And the average velocity and degree of activity molecules are basically, as I told earlier, that proportional to the temperature of the gas, right? Because like if temperature is higher, what will happen to the molecules? Molecules will be moving at a higher velocity. Am I right? Yes or no? Right? It is similar to yourself. Suppose you are very much agitated, your energy level will be higher. Am I right? Okay? Yes or no? So that means you are become hot, so that your mind became hot, so that your agitation level increases. So similarly also the molecules, right, in the gas, and at higher temperature molecule possess higher kinetic energy and system has higher internal energy. That means at a higher temperature, because the molecule will be having a higher energy level, kinetic energy, that means vibrational, your translational and rotational will be very this thing, and so also vibrational. So then you will get a higher internal energy. So if you look at these things, you will be knowing. We can sum it up like U is equal to half N F RT, where N is the number of moles and F is the degree of freedom, right? And R is the universal gas constant and T is the temperature, and this one can derive from the kinetic theory of gases, right? You must have exposed to in your plus 2 science. And if you look at the F, the degree of freedom for monoatomic gases will be 3, right? It will be only the translational, right? 3 in the 3 direction, and whereas for the diatomic, the F will be basically 5, provided it is not very high temperature, right? And for triatomic it is a 6, because 2 rotational for the diatomic apart from the 3 translational, and for triatomic it is a 3 rotational. We are assuming that vibrational form of energy is not there, right? That is the assumption, and that will be true only at a very moderate temperature, not very high temperature. The internal energy is also associated with the intermolecular forces between molecules of the system, right? There will be, if you look at, that is a in case of both the solid or liquid or the gas, there will be forces between the molecules. For let's say nitrogen gas, if I take water molecule will be having a force. They are not they try to stay together, unlike of course gas, right? And then that intermolecular forces, which because of some forces, and that intermolecular forces is basically will be strongest in case of solid and weakest in case of gas. Therefore, that is the reason why solid can take a higher stress. Am I right? Because of if his pressure is applied, the stress, it can take a stress. It is togetherness, that will be together. In the lattice structure it will be there. So if you look at, that is exactly the point I was trying to make, is here that we are the solid. Of course, this is shown 2-dimensional, but actually it is 3-dimensional. That means perpendicular to this will be having, and people have made some spring kind of a system, like where this molecule can vibrate, right? If you look at, the molecule can vibrate like this and within the mean positions, and whereas the liquid, it will be together but not really in a particular lattice structure, but it will be because of bounded by the molecule. But whereas the gas, the molecule will be far apart each other and they may colliding each other, but it will be, there will be some forces existing between the what you call molecules in the gas as well. So when the sufficient energy basically added to the molecules of solid or the liquid, what will happen? these intermolecular forces, will be reduced, and it became, overcome this thing, and it became converted into gas phase, right? Or solid also can get into the liquid phase, and this, makes the phase change process to occur, because you are adding some, amount of energy, so that they can overcome, the molecules can overcome the molecular forces. And this internal energy, because you are, having energy associated with the phase change process, is known as the latent energy, right? You must be knowing, like if I heat the water, and put a thermometer there, and then what will happen? In the beginning, the water temperature will rise from the ambient to certain degree Celsius, right? Let's say something 99 kind of things, and then after that it will get evaporated. After that there is no change in temperature, right? But however you are giving heat, and that heat will be helpful to converting this liquid into this vapor. Let's say for example water. Then that heat, that energy what we are supplying is known as latent heat, latent energy. And this is one form of what you call microscopic energy. And if you just look at the overall picture, solids can be converted into the gas whenever in a heat you supply, that is basically known as the sublimation, and gas can be converted back into solid provided you extract the heat, the energy from the gas. And when you give what you call heat energy to the solid, it will be melted out to the liquid, and we call it melting. And when the liquid, from the liquid heat is being extracted, we get the freezing, right, kind of things. We know, like nowadays very hot, you get this ice, water is converted to ice by this what you call freezing process. Similar liquid can be vaporized into the gas by adding this energy and the phase change process, and so also the gas to liquid phase change process is known as condensation. If you go in this way, that means enthalpy of the system increases, like in the upward direction. As you go to the solid, to the gas, internal energy will be increasing, so also, other terms. So, and if you look at, there will be a molecular bond between these forces. If you look at the solid, as a result it will be solid, liquid and gas, and of course there is a plasma which we have not discussed, right? These are the various phases. And but beside this, if you look at in a molecule, there will be some atom, they will be joined together having some bond energy, and then that energy associated with the atomic bond, in a molecule, we call it as a chemical energy. And during the reaction, what will be happening, that this bond is being broken, and then you will be, again new bond will be formed, and some chemical energy will be released, or it can be, if it is, released, then we call it as a exothermic reaction, because it will be giving heat. And if it is being absorbed, is known as endothermic reaction. And during chemical reaction, these bonds, new bonds are being formed, and while the old bonds are being broken. So these are basically known as chemical energy, right? And there is a nuclear energy, which is associated with the nuclear bond of atom, right? And which is quite much higher level. That means in the nucleus itself there will be various particles, and all together they are staying, and if you bombard it, and then large amount of energy being released. Of course there is a known as nuclear fission, and there is also nuclear fusion, that where the these things will be coming together, and then you will have to give large amount of heat. If you look at nuclear what you call fusion occurs in the star or in the sun, where you give a large amount of energy and a very high temperature. If you look at something maybe 100 million degree Celsius is required to have this kind of reaction in sun and other places stars. But generally it is not successful. We have not done that fusion till now. But however, the fusion reaction is being taken away, and we use some uranium kind of things, and it gives large amount of energy than that of your chemical bond. If, for example, like if you use 1 kg of uranium and then subjected to this nuclear fusion reaction, let's say U-235 kind of thing, it can give you something 6.7 into 10 power to 10 kilojoules, which is a very huge amount. And if you look at that amount, which will be equivalent to something 3000 of the coal when it is burnt, whatever the heat will be generated during the burning of 3000 tons of coal, can be obtained just by just using the 1 kg of uranium. Is very small. But however, the nuclear energy is having a lot of problems, particularly in our country where it is a populace, and one has to be very careful about the nuclear energy. And I must tell you that it is very difficult to handle any accident occurs, and because of nuclear radiations. And unfortunately, a lot of nuclear waste are coming to our country, to my knowledge. I mean, whatever I have heard, one has to be very careful, otherwise it is a very difficult place to live. And then of course, sum up all microscopic form of energy, whatever we have discussed till now, is basically internal energy, which is coined by the Thomas Young in 1807. And internal energy is basically sensible, latent, chemical, nuclear energy, right? That is the disorganized form of energy, right? These are all disorganized. It's not organized. Am I right? So therefore, if you look at the main objective of the thermodynamics, if you look at from the application point of view, that to convert this disorganized form of energy into organized form of energy, right? So that we can utilize this, whatever the latent or the nature is, basically, let me put other way around, that nature have stored some energy and we should utilize for our purposes. And the microscopic form of energy is quite difficult to measure directly, because it is very difficult. You can have a model and say, look, it is like this, but you cannot really measure. And the total energy, what we will be talking about, is not only the internal energy, but the the potential energy and kinetic energy. And potential energy need not to be confined to only gravitational potential energy due to gravity, but it can be due to other things. So the specific total energy, as I told, it is a total energy per unit mass. And as I told, that main task of thermodynamics is to devise ways and means to convert this internal energy into useful form of energy, that we call it as a work. And let us look at why we call it as a basically unorganized form of energy, right? So if you look at, there is a wheel, and this is a dam. Dam is basically like water being stored and putting a dam height, and this will be having certain amount of this thing stopped, and then water is allowed to flow through this, and it will be known as a Pelton wheel, and the water will be coming with certain velocity, very high velocities here, because it is having potential energy, right, because of height. And then this is converted into kinetic energy, very high, and when it is kinetic energy, that impinge into this veins of the turbine, you can think of, and you will get the energy. It will be rotate, and you will load it, and then you will get the mechanical energy, which we can use for our power generations and everything. But however, if I place these turbine blades, and then we call it basically belt and wheel here, right? And can it give the work done? Is it possible? So I am getting here the work done, and some power I am generating, right? Mechanical power, and then we will convert into electrical, okay, using genset. Now the same wheel I will put it here on the upstream of the dam. Can I get some work done? Yes or no? Certainly no, right? Because although the energy is there, it's having potential energy, right? It's having molecules are moving, and then it is interacting, like having this thing, but it is these molecules are coming and impinging into these wheels. But these are not it is occurring at a random manner, but here it is in an organized manner. Like it will be all this thing will be going in direction and go on impinging into the what you call turbine blades. Am I right? So therefore the microscopic kinetic energy is a form of energy, because we have converted into macroscopic kinetic energy, and which is much more useful than the disorganized microscopic energy, because these are also microscopic energy, are moving. Both are kinetic. This is kinetic energy and these are also kinetic energy, but one is microscopic form, other is the macroscopic form. So objective of basically thermodynamics is to convert this microscopic form of energy or unorganized form of energy into organized form. So that is true with a country also. Am I right? Yes or no? You must be knowing the history, right? We are invaded by various people. India was a populous country earlier also, today also, right? See, the few people came with a very organized manner, they could win over our land and rule over this. Am I right? So because we are not organized, similarly today the market forces are what you call invading our cultural heritage, spoiling. So because we are not organized, therefore we couldn't really resist the cultural invasion what we are being affected today. So therefore it is very important to learn, like that we will have to be organized, right? That's why we are having army which is organized, so that they can, nullify the invaders' intention to come to this land and then maybe create some problem. So therefore it is important to be organized in your case. For example, the education, the objective of education is what? You people are being educated or being exposed to the what you call teaching and learning for last 20 years, right? Or maybe little less, okay? So what is the meaning? Meaning is that your mind is, will be vacillating all the time. So you should have to develop your concentration level and get trained so that you will be organized in your mind to deliver some kind of work. So now, as I told that energy is always associated with the environment, and whenever we are trying to harness the energy, so it is important that we should take care of environment, and there is a global concern for the what you call environment today. And was it there in earlier days or not? It was there, but we never looking at that seriously, because we are not using the technology that blatantly. But today we are using for our own comfort, but we are spoiling, and from the energy devices, the pollutants emitted from during the combustion of fossil fuels, or like global warming and the smoke and the acid rain we are getting. You might be aware that in particularly earlier days, people were asked to go and have a good enjoyable shower in the first rain. Today people are asking, don't do that. Why? You will be in trouble, your skin will be in trouble, okay, right? So because of acid and smoke, and unfortunately our country, most of the cities are really with the environmental problems, because we are not taking care of it, and we should, as a conscious citizen, we should take care of that. And then thermodynamics comes into picture. The environment pollution are reach a very high level across the globe, and India is one of them. And in the name of development and then quality of life, we are using energy blatantly and then also spoiling. So like motor vehicles are the largest source of air pollution, and we need to devise better energy devices with the help of thermodynamics, so that we can devise better environmental friendly gaskets for our use. And therefore the energy conversion processes are often accompanied by environmental pollution kind of things. We need to take care of it. So when we talk about this kind of thermodynamic systems, we always dealing with a system which will be in equilibrium, right? And because we are dealing with classical thermodynamics, right? As I told, we are not interested in the microscopic way of the things in molecules and interacting, or not. We are basically looking at the gross way, macroscopic aspect of that. So therefore, and our this thing will be in equilibrium. And when will be in equilibrium, the equilibrium means basically state of balance, right? If the state of balance is there, we need to see like whenever the system will be interacting with the surrounding, it will be attaining equilibrium, right? And then we will find out what are the changes as occur. So in the process, that means the equilibrium means the unbalanced potentials, that means the driving force should be zero, right? There won't be any driving force within the system, then only we can look at it. That means in the beginning there will be in equilibrium, then whenever there is interaction, there will be system will be interacting with surrounding, again it will attain the equilibrium, then we will be talking about the change, right? That we will be doing in this kind of thing. And when you say that equilibrium, okay, let us understand what do we mean by equilibrium, okay? We will take this example. There is a copper rod, right, and there is a two baths. One is at 100 degrees Celsius, the boiling water, right? Temperature remain constant. Am I right or wrong? Okay, because is it temperature will change if I go on giving heat, right? Unless the last drop of water is there in this vessel, it will not change. Okay, and similarly we will talk about another bath. We call it as a ice bath, right? 0 degrees Celsius kind of thing. And this is a copper rod we have connected with the boat to start with. And what will happen here? That means this is at high temperature. This is the boiling water bath which is at 100 degrees Celsius. The ice water bath is at 0 degrees Celsius. What will happen to the heat? Heat will be flowing from higher temperature to the lower temperature because of gradient. Am I right or wrong? Now when you do that, so will it reach equilibrium? Let's say after 1 hour, what will happen to the temperature in the copper rod? Copper is a good conductor of heat, so also electricity, right? So here we are concerned about heat. So what will happen to that? Will it attain equilibrium or not? Huh? Yes, after 1 hour or after 2 hours. Maybe in the beginning it won't, right? But later on it will be, if I give sufficient time. Do you agree with me or not? How many of people agree with me? But that means few people are not agreeing, right? Few people are not agreeing that it will not reach equilibrium. Okay, so what I am considering, this what you call this copper is our system, copper rod is our system. Okay, that means whatever the diameter, length it is having, that is our system boundary, surfaces, all those things are our system boundary. So let us look at what is happening. That means if you look at here, this is a temperature, and after this thing like the temperature at point A will be here, it's some closer to the 100 degree Celsius, and B it will be in between, and C is corresponding to the lowest temperature because it is lowest is the 0 degree Celsius here, right. But that means if you look at this system itself, what is happening? The system, the temperature gradient is there because the temperature at A is not equal to temperature at B is equal to not equal to at C. Am I right? Then only it will be equilibrium. There is a gradient here. The temperature is changing. That means the heat the temperature at A will be much higher than the temperature at B. There is a gradient. So heat will be flowing. All the time heat will be flowing. That means it has not reached a what we call equilibrium. However, it has reached a steady state. Am I right? Now you understand what do you mean by steady state and what do you mean by equilibrium. Are you getting my point? What I am trying to say? I think so. Now what I will do, I will take this heat copper rod and insulate it, right, and allow it to homogenize. That means the temperature will become like this, some average temperature you will get, and uniform temperature attain, and system is said to attain the equilibrium, right. Then only, that means I need to isolate it, otherwise no. So that is basically what you call as a reach equilibrium. But unless I isolate means basically isolate it from its surrounding, and also the heat source and heat bath and the cold bath, right, those are basically surrounding for it. Am I right? So that means equilibrium means absence of any spontaneous change when the system is isolated, right. In other words, all the macroscopic properties remain uniform and constant, right, because if you look at the temperature is remaining constant across this whole range, it's not changing, right, it's not changing with respect to time as well when it is insulated. But however, the microscopic activities go on, right, the molecules will be vibrating, right. In this case copper rod, these molecules will be vibrating, but because of temperature, but however it will be temperature will be same, right. So the macroscopically it will be uniform kind of thing, properties. So when a system is in basically thermodynamic equilibrium, because we will be talking about equilibrium all the time and then looking at it, so we can say that a system attains a thermodynamic equilibrium only when it will attain the thermal equilibrium, mechanical equilibrium and chemical equilibrium, and there is another one which is basically phase equilibrium, right. We will be discussing about all those things. That means in the next lecture, right, and I will stop over here.